Welcome back. So in the last week, we understood how to analyze the electrostatics of a MOS capacitor. So we have derived expressions for electric field and voltage. Uh, in a MOS capacitor, we have drawn the profiles. And towards the end, we introduced what is known as surface potential and then the relationship between the surface potential and the gate voltage. Okay. So we'll quickly recap some of these things today. So as I've been emphasizing multiple times, band diagrams are a very, very useful tool to understand the what is happening in the semiconductor device. And also, in the last lectures, we have introduced the block diagrams, block charge diagrams. For example, how does the charge vary as a function of position in a MOS cap? Like how does electric field vary and how does the potential vary? So these are also very useful. So together with band diagrams, they convey a lot of information. Okay. For example, you have looked at all this before. Let me try to quickly recap. So if I look at the semiconductor band diagram here, what can I conclude? Okay. What are the few inferences? For example, we can look at the bulk Fermi level and then decide what is the doping. Looking at the Fermi level closer to EV, I'll conclude that my substrate is a P-type substrate. Okay. And if I look at the Fermi level, relative position of the Fermi level closer to the surface, then I can decide whether the MOS capacitor is in accumulation, depletion, or inversion. So for example, here, you see that the Fermi level has now moved above EI. Okay, so it's definitely, it doesn't look like it has reached inversion, but it is definitely depletion. Okay. So if the Fermi level moves even higher, such that the surface potential becomes 2 phi f, then that will be inversion, onset of inversion. We will discuss that in a greater depth today. Okay. And what is the applied gate voltage? Well, the applied gate voltage in this case is positive, right? The reason is whenever you apply a positive gate voltage related to the substrate here, the Fermi level move down, right? The Fermi level in the semiconductor is here, and related to that, this has moved down by this much distance. So that is a positive applied voltage. And we could also ask, is there any fixed charge in the oxide in this case? What happens when you have a fixed charge? When we try to solve the electric field in the oxide, we have assumed that, we have considered that d rho by dx is equal to 0, right? Sorry, dE by dx is equal to 0 because dE by dx is equal to rho and rho is 0. There's no fixed charge. So whenever you have a constant electric field, this is a linear gradient, right? The bands are bending in a linear fashion. So electric field is constant. And this implies there are no fixed charges, fixed oxide charges. Okay. Suppose if there was an oxide charge, then dE by dx will be some, let's say some position or some function of x. Then it will not be linear. It might be quadratic or cubic or whatever, right? If there are some charges present in the oxide. Okay. So what is the electric field in silicon? What is the electric field in oxide? Yeah, well, we know that, how to do this. Like for example, we can take the gradients here, right? In oxide, you can take the gradients. So basically, E is equal to dEc by dx, right? 1 over q. So in this, both cases, gradients are in the same direction. So electric field is positive. Okay. And is this system in equilibrium or non-equilibrium? Well, I mean, we have not explicitly showed any quasi-Fermi levels. So it looks like it's not in it's in equilibrium region. It's not in non-equilibrium, it's in equilibrium. So whenever you have EF is equal to EFN equal to EFP, right? Where your EFN and EFP are the quasi-Fermi levels and both are coinciding at EF, then it is basically equilibrium situation. So this will tell you that it's equilibrium situation. Okay. So is there any current flow in the MOS capacitor? Right? That's an interesting question to ask. So what happens? So how will the current depend on the quasi-Fermi level? We saw that it was basically mu times n times dEfn by dx, right? So if you look at the gradient in the quasi-Fermi level, you can find out But right now there is no gradient, there is no quasi-thermal at all in the semiconductor. So there is no current that is possible here. Okay, in the way that it is shown right now. Okay. Uh, so all of this information is contained in just the band diagram, and that is why it is so important to analyze the band diagrams carefully. So if you have not already done it, I would urge you to draw these diagrams by yourself. Understand each and every line you draw in a band diagram represents something physically. So if you keep doing that, take it as an exercise and repeat it, then you will understand the physics very, very well. Okay. And these block charge diagrams are also, we have seen them in the past, in the last class. For the depletion case, in this, when you want to, you have to apply a positive voltage for this. This is a P-type substrate. So when you apply a positive voltage, you push away the holes and expose the acceptor ions. So this is the depletion charge. Depletion charge consisting of exposed acceptors. Okay. And the other side, you have this is a delta function, right? Delta positive charge, because it's metal. Metal cannot have charge in the bulk, so it has to be at the interface. What interface? Interface between metal and oxide. Okay. So this is what we can figure out from the charge diagram. And of course, it's a uniform charge density. That's why you have this height to be equal to NA. That's what is given by doping. And then based on this, we have calculated how the electric field should be, right? This is straightforward. It is positive, of course, and then it is linear here and constant, right? And there is this jump here, which is very, very significant. That comes because epsilon of oxide times electric field in oxide should be equal to epsilon of silicon times electric field in silicon. This is Gauss law. So that jump has to be maintained. So that jump, we will actually run a simulation on NanoHub and show you that this exactly turns out to be true. And of course, your potential, you can always write the applied gate voltage VG should be equal to the potential drop across oxide plus we called it surface potential. Let me call it phi S. Okay, surface potential. So I think in the last class I used psi, but this is basically now I'm just using surface potential because it's consistent with other notations. Okay, so please note this change. In the last class, I use psi s, but I'll call it phi s from now onwards. Okay, so this is quadratic, and this is linear. So why each of these things turn out to be that way? You should be comfortable. All right. So this is what we did last time, and then you should do this for accumulation, for inversion, for PMOS, all of that. Okay. All right. So towards the end of the last lecture, we introduced what is known as surface potential, right? And we wanted to relate it to gate bias, and we derived an expression. Gate voltage is basically in terms of the depletion charge and the surface potential. So this was your what could call as QD, right? Depletion charge minus QD by Cox plus phi s. This is what we derived last time. Okay. So we also know that the width W is a function of phi, right? It's a function of surface potential. Essentially, what we are having is, let's say if you have, let me draw the potential diagram only in the semiconductor, I'll draw it. Let's say in the bulk you have zero potential, and this is the width of the depletion region, right? The bulk V is equal to zero, or potential is zero. So you're actually, there's a quadratic relationship here, and the voltage or potential at x equal to 0, in this case at the interface, basically this is, if I call it 0 here, this is your phi s, surface potential. Okay, that is the amount of potential that is required to be applied at the interface between silicon and silicon dioxide, such that you cause the same depletion, right? The depletion width will be whatever we give. So how do we calculate the width of the depletion region given a surface potential? Always go back, we did this in the diode case. The same expression holds. So this will be epsilon divided by QNA times the phi s, surface potential. Okay. Once we know surface potential, we can always calculate the width, and so we can substitute it back, and then finally get a relation for, I'll put QNA There's also another Q and A in this expression, so I'll write it as square root of 2 epsilon silent Q and A phi s divided by Cox plus phi s. This essentially is telling you that given any surface potential, you can find out what is the Vg or vice versa. There's a fixed relation between both of them. Okay. And if you plot it, we'll see that you'll get some expression, some curve which is looking like this. Okay, the red here. So we should remember that this expression when we derived, right, we use the depletion approximation. So we said the depletion region is flat, you know, it's abruptly changing. Okay. So essentially you have this, you know, space charge which is, if I have to, for example, here, if I go back, so this is your depletion approximation where you have a block charge like this. But we know that in reality, it's going to be something like this spread out, right? So it's going to be spread out like this, but we are not considering that. So that if you consider that sort of a depletion charge profile, then you'll get an exact solution. So it turns out that, you know, we can do a full numerical analysis of this and then determine what is the relation between surface potential and gate bias. And if you do the exact calculations, we get a relation which looks like this. Okay, we will discuss why, you know, this is important. But if you did the simple depletion, you know, delta depletion, you know, this we called as delta depletion approximation. Delta depletion approximation essentially means your depletion is abrupt. Depletion region edge is abrupt. It's not a smeared out depletion charge. Okay, if you take this approximation, we find that in the potential, you know, surface potentials in the depletion. For example, when surface potential is 0, consider that that's flat band. And as you go to surface potential of 2 phi f, okay, this is basically surface potential of 2 times phi f. Okay, when you go there, in between both of them, essentially this region is depletion. Okay, and if you apply negative surface potential, then it is essentially accumulation. Okay, and this can happen when you apply negative gate voltage. So as you apply negative gate voltage to MOSFET, you get negative surface potential. Why are we differentiating between the two? What is the difference between surface potential and the gate bias? Well, we know that the gate bias is going to fall across the oxide and the semiconductor. Whatever falls across the semiconductor, we are calling it surface potential. So there's going to be a slight difference. It's not a simple proportionality because we also have, you know, this Gauss law which tells us that there is a certain ratio of electric fields that has to be maintained. Okay, all right. And then if you cross, you know, if you apply gate voltage which will result in a surface potential greater than 2 phi f, then that regime we'll call it as inversion. Okay. So we see that whatever approximation we make, this, you know, abrupt charge approximation, that works perfectly well in the depletion part. So in this part of the curve, it's perfectly, you know, correct. But if you go in inversion or accumulation region, you see that the actual solution is telling us that the surface potential is not really dependent much on the gate voltage. So you have a large change in the gate voltage, but still reasonably small change in the surface potential. Okay, and similarly in the accumulation. So in accumulation, ACC and inversion, phi s is not strongly dependent on Vg. Okay, why this is so? I mean, we have another way of looking at it. We could think about it in terms of the bands, right? So, for example, if you look at this band diagram, when do we say that it goes into inversion? We already mentioned this. We said that the threshold definition, right? So I'm essentially looking at the same thing from various perspectives, so that you get a, you know, all-round understanding of it. So threshold was defined as when surface inversion charge, right? Let's say surface inversion charge, by which I mean, you know, this charge here at the interface. Okay, when surface inversion charge is equal to bulk carrier concentration, bulk majority carrier concentration. Okay, or rather we can call it bulk doping maybe. Okay. So if you have, let's say, we are using a, in this case p-type, right? This is a p-type semiconductor. Let's say Na is equal to 10 power 15 centimeter per centimeter cube. You have that much of bulk doping, and by applying a gate voltage, I am switching at the interface. I am getting the same amount of electrons. Okay. In the bulk, we have the holes, but I get the same number of electrons at the interface. That voltage, gate voltage, I'll call it as threshold voltage. Okay. So when will that occur? Well, we defined phi f. Phi f is essentially the distance of Fermi level from EI. So for a p-type semiconductor, it turns out to be kT by q, ln Na by Ni. We have seen this. For an n-type semiconductor, this would turn out to be minus kT by q, ln of Nd by Ni. This is an n-type. Okay. So yeah, n-type you have Fermi level higher than EI. So yeah, that will be negative by this definition, EI minus Ef. Okay. So in the bulk, you have a phi f. How many electrons should be there? Well, the number of electrons at threshold, right? This is basically, I'll say, surface electron concentration. Concentration at threshold. So what should be that? Well, if your substrate has a 10 power 15 doping, this has to be 10 power 15. And then you solve what is a phi f. Okay. It turns out that the same phi f here. So for example, here, this should be phi f. When the distance of Fermi level from EI is phi f, that is when we reach threshold. We say we reach threshold. Okay. So the overall surface potential is going to be phi s is equal to 2 phi f at threshold. Right. So we are coming to the same point as what we mentioned last time. In this here, we said that in the depletion region it is exactly matching, and we called the threshold point at which surface potential equal to 2 phi f. Okay. The reason we are doing that is at that point when surface potential becomes 2 phi f, then the carrier concentration, inversion charge concentration at the surface will be exactly equal to the bulk doping, whatever is the bulk doping. Okay. So well and good. Now what happens if you increase the gate voltage beyond that? If you increase gate voltage beyond that, we know that as you approach, as the Fermi level approaches EC, it doesn't change so much. The movement in the Fermi level is going to be slower and slower. That's why when you actually here, if you go to gate voltages higher than 2 phi f, you'll notice that it is becoming more flat response. Similarly, in the accumulation also, if you accumulate it, after a point, you don't really increase much. The Fermi level doesn't move that much. Okay, that's why we get this sort of S kind of a curve, which tells you that we don't need to really focus too much on what is this rate of change in the inversion or accumulation. Instead, in the delta depletion approximation, we'll assume that it is flat. So basically, in accumulation, if you apply negative voltage, surface potential is 0. And if you apply positive voltage beyond 2 phi f, then it is flat again. We don't really worry about the differences. Okay. All right. So now we understood what happens to the surface potential. But the actual carrier concentration is the inversion charge, right? So how will that change? So for any inversion charge beyond threshold, let's say an inversion, I'll call it, which let's say is what is this electron? What is a charge? Okay, so this will be simply Ni times exponential q phi f, let's say by kT. I'll apply instead of I'll apply an additional potential which will move my Fermi energy a little bit more. Let's say that is moving by delta V. Okay, I'll do that. I'll apply that much of extra potential on the gate. Okay, so that the phi f moves. So if that moves, your carrier concentration is going to increase exponentially. right? So this is basically additional voltage applied in inversion. Okay, so basically this tells you that if you have a small change in the delta V, or small change in the gate voltage, that is going to reflect in exponentially increased inversion charge. Okay, so this I want to summarize. I mean, you could summarize in this graph. This is not from the textbook, but another book by name Streetman and Banerjee have taken this. This is also a good undergraduate textbook. Okay, so what you see is here on the y-axis we are plotting the carrier concentration at surface. Okay, at just below the oxide, gate oxide. Okay, this units are per centimeter square. Please look at that. We have to do something to calculate this. Okay, so how does the carrier concentration change as a function of, I mean, ideally we would like to know what is the function of gate voltage, but we can also refer to it in terms of surface potential. So we have seen that when surface potential is negative, we are in the accumulation regime. When the surface potential is greater than 2 phi f, we are in the inversion regime. When surface potential is between 0 and 2 phi f, we call it the depletion. So what we see is in the inversion, the charges, the charge at the surface changes exponentially. And inversion increases exponentially. Similarly, hole accumulation, right? Hole, or PACC I'll call it, or P increases exponentially in accumulation, ACC, accumulation. So what does it tell us? We have a range of voltages in which you're not going to see that much surface charge. But once you reach inversion, it's going to be a huge number of carriers that are generated. So a block diagram way of representing this would be what we have shown last class. Okay. So if you have accumulation, you have this delta negative charge at interface. Right? And to compensate, to mirror that, there will be a positive charge at the surface, delta positive charge. Because this is majority carriers, we don't have a depletion region. We just have the majority carriers accumulating at the interface. Okay, so you have the balanced charge. But once we go into depletion, we need to keep pushing the holes away to uncover the acceptor ion. So we have to uncover the depletion charge, right? We have to keep pushing holes away. So in this case, on the surface, the charge will be varying some sort of quadratic function. We have seen the exact relationship. In a way, it is square root of phi s. Okay? When we are not yet reached the inversion part. So then this will be the behavior. But the moment you hit inversion, it again starts growing exponentially. That's why in inversion, we show this additional n inversion above phi s equal to 2 phi f. Once you reach this just at the interface, this is a delta negative charge. When I say delta, I mean that it's just at the interface. It's like a delta function. You can represent it like a delta function. Okay. So this is the way the charges behave. So I'm essentially presenting you the same information in multiple ways. Okay. So that you appreciate the physics, what's happening. Okay. It's essential that you understand this, because we will talk about CV, and then when we talk about CV, we'll use these facts. You might say, this looks okay, but this is not quantitative, right? It's still qualitative picture. So we can actually do an exact calculations of this using software tools. Okay. So here what is simulated is Consider MOS capacitor in this fashion. There's a metal, there's an oxide, there is a semiconductor, MOS capacitor. It's a P-type substrate, so it's an NMOS capacitor. Okay, and I'm showing you the plots of various quantities only in the semiconductor region. So from 0 to x0, this is basically semiconductor, right? Only in that region we are showing, okay, in different biasing regimes. And before we do that, the phi f for this simulation has been assumed to be 12 kT by Q. By the way, this is taken from this textbook here. RF is, there's a figure 16.8. If you want, you can read up about that. I just used that to draw these figures. Okay. So the substrate doping is basically 12 kT. It's a different way of representing. We are saying 12 kT by Q. So how much this equal to? This should be equal to 6. KT is 25 milli electron volts. 12 times that, right? 12 times 26 MV. Sorry, yeah, this is. So how much is this? This will be approximately 300 MeV or 0.3. Okay, this is your phi f. That means you can compute what exactly is the. I think it will be 10 power 15. Okay, roughly, because we know that 60 millivolts into phi, right? It will be 300. So it will be 5 means 10 power 15. The substrate doping should be roughly 10 power 15. Okay? You could compute it and check it out. Okay. And to that system, we apply a gate voltage such that the surface potential is just minus 6 kT. So how much is this? This is basically surface potential equal to minus 150 millivolts, minus 0.5, 0.18. So small voltage you're applying, small negative voltage. So what will happen to the charge? Well, whenever we apply negative surface potential, we're going to see accumulation. So it might not be apparent, for you when you look at it first time, but I would suggest you to just keep analyzing it and you'll get it. Okay. So when you have, why should you have a negative surface potential to get accumulation? Well, accumulation means in a P-type substrate you have to have holes. If you have to support a hole there, you have to have a negative voltage at the interface. Okay, that's why negative surface potential. So how will the carrier concentration be? So the first figure here is showing you that. This is the plot of charge density as a function of x. Okay. And what you see here is that there is accumulation. When there is accumulation, the charge density is nearly 400 times the doping density. So we have a strong accumulation. Okay. If your doping density was 10 power 15, then this is basically 4 into 10 power 17. Right? So a strong accumulation of holes and right at the interface, remember. So this distance is very, very small. This is not even 0.1. It's not even 0.1, I don't know, we'll actually see the exact numbers, but this is very, very small. It's less, roughly about 10 nanometers or so it should be, okay? 10 to 20 nanometers or something like that. We will see the numbers on NanoHub, okay? So we have this sharp accumulation just under the surface, okay? And the surface potential, of course, is this, right? We have applied, gate voltage, that's the surface potential was minus 6 kT. So, just note the axis, basically, it's upwards, negative upwards. So yeah, okay, this is fine. That is why we call it accumulation. So we have huge accumulation of charges. What happens in depletion? So we have another graph which is plotted in the middle of depletion, wherein essentially the surface potential is phi f. Okay, when the surface potential is phi f, how will the bands look like? Well, you have this, we have this, and we have EI. This is your, okay, I have to change it a little bit because I'm not able to get to this I'll call it as my EF. Okay. So this is my EI, and I'll say I have my EC. EV. Well, I mean, it's not quite correct. Yeah. Yeah, this is my EV. So originally it was close to, EF was close to EV, but then when surface potential becomes phi f, this distance is phi f. At surface it becomes EI. Okay, EF is at EI. So this is the meaning of phi s equal to 12 kT. So please, practice this multiple times. How to identify these numbers and surface potentials in different biasing regimes. Once you become comfortable, it will be. So what does it mean that it's in depletion? Well, the exact solution tells you that the charge density now, rho by QNA, we are normalizing it into the substrate, doping density. It is equal to exactly 1. It's minus 1 because the charge is minus, right? So minus 1, and then it decays like this. And what did we approximate? We use this particular line, right? This is delta depletion approximation. I mean, it's not actually capturing the decay at the edge of the depletion region, but it still gives you a lot of physics correctly. Okay. And so that's why we keep referring to this as uniform charge density, right? So QNA all the time. And that is exactly what you will see in the simulation. Okay. And of course, surface potential this time is 12 kT by Q. Okay. So how much is this? 12 kT by Q should be equal to surface potential is 12 kT is again back to the same thing, right? 300.3 volts. I'm writing phi again. Phi s is equal to 0.3 volts. Okay. So this is what happens in depletion. What happens in inversion? Right at the point where surface potential is equal to 2 phi f. In this point, your phi s equal to 0.6 volts. 2 phi f. Phi f was 300 millivolts. So this is 0.6 volts. When you have that, you look at this. You have the depletion region, right? This is your original depletion region. And there is a very sharp spike here. And the peak appears to be exactly at -2. Why is that? The reason is at phi s equal to 2 phi f, n at the surface, ns I'll call it, okay? Electrons at the surface equal to Na, right? That is the definition of threshold, correct? We have repeatedly told this. So we have Na contribution from the background, the space charge, and another Na contribution from the inversion charge. That's why exactly this peak is -2. Of course, here this thing is 24. Once you reach threshold, you see there is a big difference. When of course there's no applied gate voltage, there's no depletion at all. I didn't show you that. Okay. So once you go halfway through depletion, your depletion width in this case was 0.5 microns, so 500 nanometers in depletion width. And if you go here, there is a slight increase, but about 0.6 or 0.7, it has become, we can take that as a depletion width. Okay. Because we have increased the gate voltage, so depletion region is going to expand. But once we do that, you add now another deep inversion. Essentially, you add another 150 millivolts. 6 kT is 150 millivolts. So this is phi s equal to 0.75 volts. Not a lot of difference. Okay, we went from here 0.3, right? This was phi s equal to 0.3 volts. From here to 0.6, we essentially doubled it, and we saw that the depletion region has changed by maybe about, I would say, 30% or so. Okay, and there's an inversion happening. But once you go there, even if you change by, let's say, 150 millivolts, so not a very large amount, but you see that the charge density has spiked up. See here, so this is reaching up to 400, -400. There is a jump here, by the way. Okay? This is a jump in the axis. So jump in. This is the way you represent whenever you want to represent large number. Because I plot it in a linear scale 400, then you will not see the depletion charge. So this is a jump. Okay. So what you see is, if you go into deep depletion, or you go into after inversion, if you increase your potential, there's going to be a huge inversion charge that appears at the interface. Okay. And the depletion width does not change so much. You see here, depletion width does not move much. When you compare this to this, there's not much of change in the depletion width. That is very, very important for us. Okay. Once you reach inversion, we say that the depletion width doesn't change. All right. And we have corresponding surface potential as well. Okay. So this is the exact solutions. So please take some time and analyze this data. Okay. These graphs are very, very useful in understanding the physics. Okay. So this quadratic shape, we have very multiple times we have talked about it. Quadratic potential. All right. So before I stop this video, I just want to briefly talk about the depletion width. So we have seen that as you increase VG, right, your depletion width is going to increase. But it turns out that we have seen here, once we reach the inversion, the depletion width does not change so much. Okay. So that's why we say that we define a quantity which we call as maximum depletion width, which is given by W depletion max is equal to W depletion when phi s equal to 2 phi f. Till phi s, the surface potential is equal to 2 phi f, depletion width keeps changing. But once we reach phi s of 2 phi f, then it won't. Okay. So the way to calculate that would be, we have seen this expression. So let me see. W depletion equal to square root of 2 epsilon silicon divided by Q and A times phi s. For phi s in the range 2 phi f. 0 to 2 phi f, this is the expression. But once you have crossed that, this becomes 2 epsilon silicon divided by Q and A times 2 phi f. For phi s greater than or equal, for greater than or equal to 2 phi f. So we are taking the depletion width as not changing. We are reaching the maximum depletion width. And why does it make sense? Well, it makes sense because after, when you say that inversion has reached, right, you essentially have these inversion charges appearing at the interface. Now, if you further increase the gate voltage, what happens to the inversion charge? It will quickly respond because this raises exponentially, right? We saw that in the inversion, the charges increase exponentially. So as you keep increasing gate voltage, they respond, and the depletion width does not have to increase. Okay. So inversion charges increase in response to gate voltage, but W depletion does not change. Okay. And I just calculated the W depletion, the maximum depletion width for various concentrations. What I want you to take home here is that the depletion width is only about, I would say, 0.1 to 1 micron typically, or even lesser sometimes, maybe even 0.05 microns, 50 nanometers to about 1 micron. Okay. So that is a depletion width that you can have for typical doping concentrations and not more than that. So we will have a 500 micron semiconductor wafer, but only the top micron is where most of the physics is happening. So it's like a purely surface phenomena. All right. So I'll stop the theoretical part of the video right now. In the next video, I'll solve a few problems. I'll introduce the concept of threshold voltage one more time. I'll review it, and then I'll solve a few problems. Okay. I'll see you there. Thank you.